video for class 10. We're going to deal with rolling elements, rolling element bearings. This is part 1, and we're concentrating on life and reliability. And this is in chapter, find the book. Is it chapter 10? That's my recollection. Chapter 10, and we deal with bearings. Nope, that's springs. Here we have bearings in chapter 11. Okay, so we're beginning chapter 11, and let's get introduced to what bearings are. Okay, so there's lots of different types of these rolling element bearings. I should point out that we aren't covering them, but another type of bearing are journal bearings, right? So we might make this distinction, where a journal bearing uses a film of oil in between a bushing and a shaft that's rotating, and that film of oil is what carries hydrodynamically, carries a shaft, right? But now we want to support a shaft with these little elements. Most often we think of ball bearings, but we could also have cylindrical bearings, and they can have these little tapered bearings. So we'll take a look at that. So first, I want to take a look at a bearing arrangement, or a typical bearing arrangement here. This one is showing some cylindrical bearings at these two spots, and then a ball bearing right in there. And it seems to me that's not really typical that you would have them next to each other, but you could. But anyway, you can see how we have a shaft and how the bearing fits into this position right in here, and it's bolted into place. Something else that might be important, we also might have seals involved. So there might be, because there might be some type of fluid or pressurized thing inside here, like oil. We could possibly have some oil in there. So I think it's a good idea to take a look at a real bearing, to try to get familiar with them. And here's one out of this little horse, this I can't remember how many horsepower my little motor has. I think it's like 5 horsepower. It's a little 5 horsepower motor, and you can see here is a ball bearing that's inside there. You can see that there's individual little balls put into there, and there's like this raceway. You can kind of see the raceway. And there's a groove inside this inner raceway, and there's a groove on this outer raceway, and the balls run through it. And there's a little bit of lubrication inside there, sometimes grease or whatever, but also this engine has a lube oil sloshing around there. So the lube oil can get, because it's getting sloshed around inside the sump area, that's what we call there, oil can get inside there. And it moves pretty. They used to call these frictionless bearings. Now there is a certain amount of friction right there, but you could see, and this is sort of like press fit into place. There's a I can't get this out with my fingers right now. Now what we might want to do is we might heat up this. This is aluminum, this housing piece, and then this thing would slip right out. If this got warm, it would expand. And this might get a little warm, but this thing would expand. Well, aluminum expands more than steel anyway, so it would be easier to take this thing out right here. On the other side, you can see that it has like a little seal right in here, right? So this is very cheap type of method. This engine only costs like $97. I really like telling people that, and then looking in and trying to price out what each of the different pieces is going to be. It's pretty amazing that you could get it for $97. So let's see, I think it's still as a presentation right there. So there's many different little things that in terms of details you might want to sort out when looking at these bearings and how they're attached to the housing and they're supporting a shaft. Different types of ball bearings you could see. Here's right there, you can see this is the raceway right in there. So I like this figure right here. We're going back to it and talk about what the point of it is right there. But you can kind of see that the raceway isn't identical in terms of its radius right there. There's a little bit of slop, so you can't really quite tell it from right here. But there is a little bit of a slop to it, and you'll see that one of the main two main types, and really the only ones we'll deal with, are the deep groove and the angular contact. And really, the angular contact, kind of like you see, that it's actually there's actually a little bit more slop in here, And that's my way of thinking of it, and it's actually touching at a surface right here and touching at a surface right there. So there's sort of like the line of contact of where it's touching in the raceway is like skewed over there, and that allows it a little bit more flexibility in terms of the amount of shaft deflection, angular deflection that's allowed right in there. We'll take a look at my wonderful little shaft thing right here. Right, so this is the one that I use for gears, but we can see that I've just made it very simply, put the balls, the ball bearings and roller bearings that I have right here into this like little pedestal kind of housing right here. But we could take a look, and you can see that I have printed these out, and we're going to pass these around in class and take a look at them. This was printed as at one time together, like they call that in situ maybe, and I think actually, and it is not perfect, right? So but it's actually pretty remarkable that it can be printed out there, and it took quite a bit of like breaking this apart, right? Because there was a little bit of a support material that was involved, and they did kind of stick to each other a little. I had to monkey around and try a bunch of different tolerances before I could get these to go. But you could see, but in this, you could actually kind of feel a little bit of the wiggle right there. You can see this one actually is a pretty good tolerance. I got another one where maybe they have a little bit more tolerance. Yeah, you could feel that there's some wiggle in there. So it's not exactly like this. The groove is got a larger radius than the ball does. You could also might even be able to tell the amount of, maybe feel a little bit of the angular deflection that you would have, right? So this thing could actually have a certain amount of flexibility. So if you can imagine this thing dipping down right there, it has to have a slope at the end. And the bearings can withstand some of that. Now, as opposed to these others, now I've also made what I might call these like more like instead of cylindrical bearings, these are almost like little needle bearings, or even these are actually little dumbbells that are in there. I saw somebody else's design, and so I kind of mimicked it, and you can kind of feel a little bit different. These don't do quite as well. Well, this one actually might even actually do pretty well, but cylindrical bearings in general, they don't do as well for the taking up any amount of like that deflection. But they still can't take a deflection. But what they can't do, when it's just a regular cylindrical bearing right here, it doesn't do a good job at all of taking up axial. Whereas this angular contact bearing does a pretty good job of taking up some amount of axial thrust, right? There are bearings that are specifically for thrust. That's all they do, right? But you can also see that some types of roller bearings, they might have a taper to them. And I have an example sitting around somewhere. I just brought it over here. Yeah, here you go. So let's take a look at this bearing right here. You can see here, this one has, and I can't tell if these balls have or these rollers have taper to them, but you can see that they're arranged in such a way that they will take a certain amount of axial loading onto them. But mostly they take radial loading, right? So they're supporting something in this direction, but because they're at an angle, they can support something in that direction. But you can see something like here. Here's one that's broken, but this is a needle bearing. It doesn't have the inner race onto the thing, or maybe it was one that was designed to run in a shaft. I don't know if that's not usually typical, but you could see that these are like, maybe we would call these needle bearings, right? Because they're very, very thin, the little cylinders that were run into there. It's like other bearings that I could pass around right here. Now here's a ball bearing that's built into a pedestal, right, so that you can mount it someplace. And also you see there's a grease fitting so that you could pack it with grease, and it's sealed right in there so that you can't see the balls that are running in there. And I thought about breaking it apart because I got his little brother over here, so I was thinking about, but somebody has beat the hell out of this thing and tied that in there, and I think I'd have to do a fair amount of destruction to get this on here. This was just laying around downstairs. But anyway, it's another pedestal you can see here. And I think some of this is you could feel the smoothness of this, but maybe you could also feel some of the amount of play that's available as part of this thing too when I pass it around. So anyway, there's like your introduction to roller bearings that you can see. So now you've seen some of them. So now when we talk about the specifics of them, they'll seem like real things. So now this contact stress that takes place in a roller bearing is a lot like having this cylinder, even like on a flat plate, but now we could have a cylinder inside this raceway right here. And there's this elliptical contact area as they're drawing it in. Down below, and this is called Hertzian stress, just like we had in gears and contact stress. And some of the idea, these things are rolling, and they're pushing against these surfaces as they're supporting the load, transmitting the load between the shaft and the housing. Right there, they're the intermediary. And what can happen is you could have, from that fatigue, you could have a crack that opens up, right? Fatigue and cracks should go hand in hand with each other. But this is like contact stress. And you can see that they could get oil inside this crack, and then some more pressure happens onto it, and we get a little chunk that comes out. So that's like the type of failure that takes place. And we had these little spalls, they call them right here, where we have little chunks that have popped out, and they eventually that can make the thing run so roughly that it'll sound like it's got marbles or something inside it. Sounds like it's gravel inside, and you have to replace these. So there's a life. Inevitably, there's going to be a bearing life. And in order to describe it, we come up with a rating. We say that these bearings, the bearing manufacturer says that bearings are rated for a certain amount of life, and it varies with what manufacturer a little bit, right? There's some manufacturers that are consistent, but there's a couple of manufacturers perhaps that have their own standards. But what they basically do is they decide this is the amount of life at a certain load that a bearing can stand when 90% of them survive, all right? So when 10% fail. And so a lot of times what they'll say is the rated life is 1 million revolutions, right? They'll just say, all of our bearings, when we give you a number in a catalog for how much load it can withstand, it's based on the thing revolving 1 million times, and that 90% have survived, right? So sometimes there'll be a capital L with a subscript 10, and that's what the rated life is going to be. So let me switch over to my hand notes right here. Let me check and see what my time is on here. 13 minutes in. We're talking about life, and these page numbers are probably for the 10th edition. I don't know. Maybe I did them in 9th edition. But we say that rated life is when 90% of the group survives, and we say that it's for 1 million cycles. So we define life a lot of times, the capital L, they mean revolutions. If it's this cursive life, which I jokingly call Laverne, because there was a character on Laverne and Shirley, which was a 80s TV show, 70s or 80s TV show, with the lady who named Laverne always had monogrammed on all of her shirts this capital L, like for Laverne. And anyway, that was going to be for hours, right? So what we want to do is have a relationship between life and load. All right, so they found from experiment, and that's what all these little dots are going to be. They drew a straight line through there, and they figured out that if you take an exponent right here, that's 1 over some number right here, and you raise L to it, that you can draw this straight line through this thing on a log graph. Right, and they have found that that's going to be a constant for a particular bearing. And they found that ball bearings, the exponent could be 1 over 3, and for roller bearings, they use 1 over 10 over 3. All right, so 1 over 3.33333, right? And this is like a statistical thing, and maybe we should like maybe make it look a little bit more statistical right here. So there's like a cloud of data. They drew a line through it, and this line right here only has like about like a band right here, where they're saying that like here you can think of that as being a band that says 90% will fall inside there. There will be some that fall out, right? So that's what you can think of as they're doing that. They made tests and they ran machines with under different loads, and they figured out what the life is going to be of them, and then they said, well, okay, we're going to use a particular life right here, that 10 million right there, and boom, we're going to have a rating right here. So that's going to be the F that corresponds to that L. What we end up, what we want to write down for this, and these are approximations, right? This is just a slope that they found, and it trends, and it seems to be pretty consistent, repeatable. So what they like to write down, they like to come up with these subscripts for each of the L's and the F's. All right, so the load is F. We're going to use lowercase n for RPM. The subscript with an R means that's what's out of the catalog, right? And then now instead, well, we might want to have it, we might have a different loading scenario than what's in the catalog. So we need to match an apples to apples type of thing with our scenario to what's in the catalog. So we're kind of going shopping, and we're going to try to interpret what's in the catalog or change our scenario so it's something that we can pick out the correct thing out of the catalog, the correct bearing. So we see that there is a relationship if we just use this idea right here for the rated one and the life right here, and we raise it to the 1 over A, we can say that it's going to be equal to our desired load times our desired life, 1 over A right here, okay? And just so that we can make a connection between life here, just recognize that we can say the number of revolutions is going to be equal to 60 times the number of hours times the RPM right there, right? So that's an important equation. So if you were dealing with revolutions, we use capital L, but a lot of times we will be given the number of hours. We need to know the RPM, multiply it by here. So just to recognize, I mean, it's a pretty simple formula, but that's what we're using when we want to talk about hours. We use this Laverne, and we calculate here. But when we're actually calculating this thing out right here, this is in terms of number of cycles. So we can, there's a number of different ways. There's a bunch of different equations in the book. We could say this is equation like 11.3. I like to have just a single equation that we can try to use, right? So, but let's write down what's in the book, right? Because that's usually what we're dealing with. So what they say is they call something a C10, which is their thing they call, this is the catalog rated load, right? So I already have that written here. The catalog rated load, what they mean is FR, right? They mean it synonymously. They'll say, okay, so we're going to take a load that we know in our scenario right here, and they're going to take the desired life that we're going to have, and we're going to have the rated life right here. And this LR is usually somewhere in the book, in the catalog. They tell us what it's based on. It's most often going to be 1 million, but we'll see there is at least one manufacturer that does it differently. They use 90 million instead. And another way to write this equation right here is to say that it's the load that we desire, and we could say this Laverne times the RPM of the desired divided by 60. And I'm going to veer, this is not how it's written in the book, but we'll just say it's just the rated life. But we can, we can also use the equation not just for shopping in the catalog, but like if we want to say, hey, we used this bearing in this situation for this load and this number of cycles, if we switch it to this number of cycles, what's the load it can handle? Or what's the rating? Okay, like we say, okay, instead we want it to last this long. We know it can last this long. How much load can it handle if we're just going to use a smaller amount of time? But we can have this right here. Now, what we could write, and it might be easier to think of it, is this ratio of time. A lot of times they call XD, right there. And another way to write this, or maybe we should include in here, I think it's a good place. They put it in later. So they write this equation a bunch of different times, just in the book. So I think it's good to put the application factor right times that, and then just say XD raised to 1 over A. So I kind of think this is more of a generic type of thing. And then we can also see that we can adjust this XD for this scenario here. So I think I've taken a long enough video as part of this. So I'm going to make a break right here after 21 minutes and then have an example. Because I doubt many people will listen to this first video, but I'd like to have it anyway.